Hi everybody, and in this tutorial I want to focus on a bit of a deeper application to math and physics than what some of the videos have gone over so far. And this is going to make an explicit use of the integration technique that we have done in previous videos. And this is the issue of finding Fourier coefficients. Um, and this technique is extremely powerful for extracting information out of physical systems that may otherwise be very difficult to analyze. And the idea behind this is more complicated than what we're going to get into in this tutorial, because I actually want to show you how to do it and how it relates to the computational side as opposed to the mathematical theory behind it, which is very rich and somewhat dense. But the idea is this: if you have a function f of x, this function needs to be a well-behaved function, okay? And what do we mean by well-behaved? Well, it can't have weird discontinuities, and the derivatives have to be defined everywhere on the interval that you are thinking about or trying to calculate the function on. But as long as it's a well-behaved function, then you can expand that function in a series of what we call complete functions. Okay, so if your f sub n series of functions is complete, okay, and completeness by definition means that you can write any well-behaved function as a series of these complete functions. Then what's going to happen is each of these complete functions, now n here is going to be an index, right? For folks who might not have run into this type of function before, n is just an index, and so all of these f of n's are going to have a similar form, but they will differ in their argument somehow, okay? But they're going to differ by that index, right? And we'll see actually what this means here shortly. But the arguments are going to differ by that index. And so the strength of each contribution from each of the individual functions in the complete set that contribute to the overall well-behaved function are given by what are called the Fourier coefficients. So it is the Fourier coefficients that we want to calculate. If we know what set of complete functions we're going to use to expand our well-behaved function as, then what we need to know is the strength of each individual contribution for each of those functions. So the coefficient here, Cn, is what's called the Fourier coefficient. Okay. And typically these indexes are going to start at 1, so n will equal 1, and it'll go up to infinity. And so the idea is when you multiply the correct coefficient with each function in your complete set, and then add everything up, you sum it all up, you should get your well-behaved function. And to calculate these, this is where we're going to kind of hand wave over the math and skip why this works. Because again, I want to show you the computational side of it. But to calculate these Fourier coefficients, what it turns out is that the Fourier coefficient is just equal to the integral of each individual function in your complete set multiplied by your well-behaved function, and your integration is going to be over the interval over which you are considering your well-behaved function. Okay. I know that that's kind of very vague, but I will mention this about this integral. This result rests on the idea that when you have the integral of two of your complete set, two different functions in your complete set, and you integrate over both of those, your result is 0. Okay, if n and m are different, so for example, like if you're going to integrate your first index or your n equals 1 function from your complete set and your n equals 2 function from your complete set, and you integrate those over your specified interval, then your result will be 0. Okay, so that's one of the conditions of a complete set. And the reason that works to get this coefficient then is because if you just multiply both sides by f of m x, and m and x here are just dummy indices, so they can represent any value we want. Okay, m and m, there's no deep mystery here. So n can be 1 through infinity and m is 1 through infinity. They're just different. All right. Or they don't have to be different. In fact, the proof rests on the fact that something happens when they're not different. And so when you multiply both sides, if m and m are not equal, your integration is 0. So when n and m are not equal, this entire right-hand side will be 0. And if this is 0, then the left-hand side is 0. But if n equals m, then the integral of fn of x times fm of x dx is equal to 1. And so if all of this is equal to 1, then Cn is just going to equal the integral of the index of your complete function, for which is equal to n, and therefore you can come to this conclusion. Okay. So that's a little bit of the math background. There's more to complete functions than this. But as one of the physics texts that I have on quantum mechanics that talks about this says, the proof to show that a series of functions is complete, or a set of functions is complete, is rather laborious and tedious and very cumbersome. So most physicists assume completeness and hope for the best. But we do know of some elementary sets of functions that are in fact complete. And again, we're not going to go through any of the proofs or the derivations, but I will apply this to a specific example, and then we'll see the code that I've written, and we'll break that code down. So this is a standard problem in quantum mechanics, and the problem says, suppose you have a particle in a well that is initially of width a. So I have a barrier at x equals 0 and at x equals a, and outside that barrier the potential is infinity. So what that means is when you place the particle in this well, and inside the well the potential is 0, the particle cannot penetrate out of that well. Okay, so this is a hypothetical situation, but what this does, what quantum mechanics does then, is it allows us to calculate the wave function for the particle in this original well. And it turns out that the wave function for the particle in the well, when we don't have any time dependence attached to our situation here, the wave function turns out to be this equation right here. Okay? And notice here's where the n index plays a role. Okay, so each wave function is going to be the square root 2 over a just has to do with the width of the well and what we call normalization. Again, we're not going to worry about normalization yet. Maybe we'll do normalization in another video shortly, because normalization also has to do with integration. But each individual wave function here can be written as square root 2 over a times the sine of n pi x over a, where n is our index, 1, 2, 3, 4, 5, etc., etc., etc. A is the width of the well. And if the particle is in what we call the ground state, then its wave function will be shown as in green here. Okay? And the wave function is important because what the wave function ultimately does is describes the behavior of the particle, number one, and number two, describes what we would observe if we made a measurement with what we call an observable, right? Since we can't actually see the particle, we can't actually see the quantum cloud that it creates, but we can do things like measure energy and things like that. So what quantum mechanics tells us is if we know that a particle is in a definite state, then when we make a measurement with an observable, we will obtain a specific value or a specific set of values. And when you have a particle in the ground state in the infinite well, the ground state is the lowest energy state, and that is written by this equation here when n is equal to 1. Now I've put the prime here on these wave functions to denote that they'll be different than the wave function that I'll describe here in just a moment. But so this wave function with the first index just sets n equal to 1. So this is the wave function as described by the green line here. So we're assuming that the particle is in the ground state. Okay? And if I were to draw the n equals 2 state, psi of x equals square root 2 over a sine 2 pi x over a, that wave function would look something like this. Okay? So, in other words, the green is essentially half of a sine wave. The second level, or the first excited state, if you will, the n equals 2 state, is a complete sine wave. The n equals 3 state is when you would have three, for lack of a better term, antinodes. Okay, so in the n equals 1 state, you've got one antinode right here. In the n equals 2 state, you have an antinode here and here. So another way of thinking about the n index is the number of antinodes that you would have. Okay. And so you would have something, if my drawing skills will do me justice. Okay, so that would be something like the n equals 3 state. But we're going to assume that the particle stays in this ground state. Okay, so we're going to just focus on the green line there. And the problem says this. Imagine you have this particle in the well, and then the well automatically expands to twice its original width. But the particle hasn't had time to adjust yet. So if the well expands to twice its original width, like this, then what's going to happen is the particle is going to have its original wave function from 0 to a, just as it did in the previous part, but then from a to 2a, it'll have a value of 0. So this is the new wave function in the expanded well. And this is why I wrote a prime on the original function to differentiate it from the state in the expanded well. But the expanded well has states very similar to the complete set of stationary states in the original well. It's just that they're written with twice the width. So instead of square root 2 over a, my coefficient would be square root 2 over 2a. Now, of course, that reduces to just square root of 1 over a, but I wrote it out explicitly so you can see. And then 2a appears in the denominator here. So this is also a series of functions that depend on n. So this is a complete set. So the claim is this. We can write this piecewise function where the state of the particle is now in its original state from 0 to a and is 0 from a to 2a. We can write that as an expansion of these new states. So that's what this equation is claiming right here. Okay, so and this is the same equation that we had right here, right? So to find the coefficients, you just multiply both sides by the indexed function from your complete set for each value of n from 1 to infinity and integrate, and that will be the coefficient. So it turns out in this case, you need to multiply each individual function by your original wave function over the interval 0 to a, because that's the interval over which that holds, and then multiply 0, because that's the interval over which this one holds, from a to 2a, multiplied by your complete set, or each function from your complete set. And so it turns out, of course, that when you multiply any function by 0, it'll be 0. So this term cancels out, and you're just left with this piece, which is this written out. And let me take that back. So this is what we're going to program. Okay, this is what we're going to program. And of course, we can simplify this a little bit. So first note some things that we're going to do. First of all, we're going to set a arbitrarily equal to 1. So that will simplify some things. And when you do that, this is just going to be the square root of 2. And the second one will just be 1, right? Because the 2 divided by 2 is 1, and if 1 over a, if a is 1, then that's 1 over 1. So we're going to basically, the integration, the meat of our algorithm is going to be multiplying our original wave function by each of these stationary states. And just like we had in the original well, these stationary states for the expanded well, the n equals 1 is going to just simply be, that's terrible. Half of a sine wave, and the, let's keep red. The second will be one complete sine wave. Okay, and the third would be something like this, and so on. Okay, so these are just longer versions of the states in the original well, right? And that they're expanded because of the 2 in the denominator here. That expands the argument. And so what the claim is, the function in green here, this piecewise function, can then be written as the sum of these expanded states if we know what the coefficients are and we calculate the coefficients with this integral. Okay? So that's what we're going to do. So I've embedded some code in Python Baba, and so instead of typing the code out piece by piece, what I thought we would do is I would show you what the code looks like, and then we would comment on the code as we went along, so that way you can see exactly what I did and why I did it. And to explain just a little bit, first things first, if I run the code as is, this is what I get. This first plot just represents the state of the expanded well. Okay, this is the same plot as the green in this graph right here. Okay, and the second plot shows the expanded wells series of complete functions, as many as I've plotted. Now I've only plotted the first 2, but you can see the first one is just half of the loop, or half of the sine cycle, and the second state is the full sine cycle. The third actually is after we have calculated the coefficients and we start to add them together. So what this one does is recursively add each new result as it comes in. So since I have 2 states, what I've done is it adds the final result here adds all of the states before it up to and including. So it's adding the green wave plus the orange wave. Now, the orange wave remains unaffected because it just simply plots it on there, and then it plots the sum of the both ways. But you'll notice that the amplitude down here is much smaller than here, and that's because some of the orange is above the axis and some of the green is below the axis, so they're canceling each other out. And that's what we want in this region, because we should get a flat line here. We want a nice bump on the left-hand side of the well, and we want it flat on the right-hand side. And even after only 2 terms, you can kind of see that this is potentially the way this is going to go. We have a nice bump that kind of resembles what's happening in the left side of the well, and it's starting to flatten out a little bit right here. And if I run with more terms, okay, if I run this with more terms, you'll see that it actually starts to really flatten out, right? So even with just a few terms in the series, it actually starts to approximate the original function fairly well, okay? Which is really interesting. So what we'll do is we'll go through and we'll comment on the code as I've written it, and we will then see what happens, right? And hopefully this will make some sense to you. Now, this is by far not the most efficient or elegant way to do this, okay? This is not the most efficient or elegant way to do this. This was more of a, what I like to think of as a brute force method, okay? Where this kind of goes through the logic step by step. So this is not what we would call, quote unquote, a Pythonic way of doing this. This is more a brute force. If I kind of step back and look at the math step by step, how would I code each individual step? Okay, so this is actually kind of like driving a route on a highway, right? You're passing each mile marker as you go, instead of looking at the problem as an entire picture. This was done passing each mile marker as you go. Okay, so just be aware that there are other ways, and probably more elegant ways of doing this. But if you understand what this code is telling you, then it will probably make more sense to do some of the higher and more efficient methods. So without further ado, let's get started. Okay, so of course this first line, we're just going to import our libraries. Okay, that's what this first line is for. So remember, the pound sign means comment. The interpreter won't do anything with this. So this just imports the numpy and matplotlib libraries for math and plotting capabilities. Okay? Okay, so n is the number of data points over which I have split up my x-axis here. So this is the number of data points that will go into the integration. Not exactly, okay, because if you remember, the Simpsons method is n minus 1 over 2 actual number of steps, but this is the interval over which we have split the x-axis that will be taken into account. Okay, so n is number of points along the x-axis, and we have set the width of the well to 1. Okay? All right. So, if you remember, x is the width of the original well, which was from 0 to 1, or from 0 to a. Okay? And this is why this was not Pythonic, and this is why this was kind of a piecemeal thing. But again, a brute force method that, as you go through it step by step, might make some sense. I labeled x3 here because I programmed the algorithm to do the integration first, and I used a variable called x2 there. But x2 and x3 have the same length. Okay, so x2 also runs from 0 to 2a, but it has 2 times n minus 1 points, because I want the interval of my increments for each point to be the same as for my original array in the original well. And so that's why this is here, but again, we'll kind of explain that here in just a minute. But I done this, which this actually goes into the integration. This is the interval used for this plot and this plot and this plot. And I'd already labeled it x2. So x3 is the space, or let's call it the x values from 1 to 2 for which the function is 0. Okay, so that correlates with this portion of the graph. All right, so this was x1, this is x3, and then x2 is over the whole thing, but using the complete sets, or the complete function. Okay. And then y is the zeros from x equals 1 to x equals 2. Okay, so this set of zeros is just this part of this function, right? So it stays by itself. Dx is the increment along the x-axis. Now, remember, okay, so we have 1,001 points. So we have 1,001 points from 0 to 1. That's what this line of code says. Okay. So remember that your index for Python starts at 0. So the first number at 0.0 has the index of 0. Okay? And so then my index of 0.001, which is the next number, would have an index of 1, and so on. Okay? And so what that means is that my increment here is going to be 0.001, because my first element is going to be 0.001, the first indexed element is going to be 0.001. The 0th indexed element is going to be 0.0. Okay. And so that's why we have 1,001 points here. Because to go from 0 to 1,000, if I want an even increment like that, then I need 1,001 points. Because it would be 1,000 points to go from 0.001 to 1,000. And the extra point is for that 0.0 point there. So the increment along the x-axis is going to equal 0.001, and that just helps keep the computations clean. Okay? So psi prime is the original function. Okay? That is this function right here. Okay? So psi prime is going to equal the square root of 2a times sine of pi x over a. So np square root 2a. Now again, because we set every a equal to 1 and so forth, you can drop, the a's if you want, and this would just be square root 2. On the other hand, if you leave your function with this coefficient in this form, then you can adjust a here however you want, and you don't have to retype this line of code. So that's why I've also kept it in this form, even though I could simplify it in our particular case. But the original function was square root 2 over a times the sine of pi x over a. And again, the NPs are here because we've imported numpy as NP. And so what we're basically saying is I'm going to draw these functions, the square root function, the sine function, and the number pi from the numpy library and implement them the way that numpy implements them. Okay. Now, in practice, there's usually very little difference between the numpy library or the math library with these types of functions, but there could be minute differences. And if you have really long sets of code that run over several different iterations, if there are slight differences in the way that each library calculates, for example, the sine function, then those differences could build up over time and may give you different results. But in any case, this is our original function. Okay. And so this just generates the first plot. Okay. So we're plotting the expanded well function, but the original wave function and then zeros. So this plot is once again this piecewise function right here. Okay. So if you're running out of room, you can see the comment is still there. Okay, so now we're going to kind of get into the realm of the actual meat of the integral. Okay, and so remember that Simpson's rule runs from n minus 1 over 2 of your total number of points that you have taken into account. So since we've set the x-axis to be 1001 points, then that is the integration over which we are going to go. Okay? That is the integration over which we are going to go. So, with that in mind, yeah. No, let's call it calculations. So we're using Simpson's method for the integration. Whoop, I didn't want to do that. Okay, so these are going to be placeholders So the psi, setting psi equal to 0, when we go through the first integration and calculate the first Fourier coefficient, okay, that will give us this, and then it will give us, technically it'll give us this, and then it'll give us this, and then it'll give us this, and the psi total is what we're going to add each of these to finally get the result right here. Okay, so these are placeholders for the integration in the algorithm. Psi will calculate each individual wave, and psi total adds them consecutively. Okay. So now, x2 now represents the number of points along the x-axis that we will integrate. And so since we've set a equal to 1, we're integrating over the entire 0 to 2 range. And the number of data points, okay, 2 times n to the negative 1. I really should say that this is not the axis that will be used for the integration. That's already set right here. So this is the x-axis used for the expanded well. Let's put it that way. Okay. So it's twice the width of the original well, which was from 0 to 1. And this 2n minus 1 ensures that the increment will be the same length, right? Because I need 2001 points now if I want the increment to stay the same. Because, again, if I start at 0.001, it would take 2,000 points to get to 2,000. But the indexing starts at 0. So that gives me 2001 points. Well, 2001 points is 1 less than doubling n. Because if I just double n, then that will give me 2002 points, and that will give me a slightly different increment than what I've calculated with this line of code. So to keep the increment the same, I'm subtracting 1 off. So now this will be 2001 points with same dx as above. Okay. So I've doubled the width of the well, and I've doubled the number of points, except for minusing 1 for the indexing issue. So m equals 5. M is 1 more than the number of coefficients we want to calculate. And again, this starts with, or this is because of the 0th indexing issue. In our series, we want n to start at 1. Okay? In our series, we want n to start at 1. But in Python, indexing starts at 0 unless you specify it otherwise. But because the 0th coefficient, there is no 0th coefficient, we can just go ahead and call the 0th coefficient 0, and it does nothing to our code. So what this is going to do is going to evaluate our algorithm, if you will, and the 0th index for m is going to be set to 0 anyway, and then when n equals 1, you will get a number. Why is that? Because when I put a 0 in for n here, the sign of 0 is 0, and then I would have 0 here times my psi prime of x, and that sets the C0th coefficient to 0, and it doesn't affect our algorithm. If that coefficient didn't disappear, for example, if this were a cosine function, then that would not necessarily disappear. And so you would actually have to manually set the coefficients to start, or the algorithm to start from the index of 1 and not 0. And there are ways you can do that. But since the 0th index doesn't affect our calculation anyway, I went ahead and set it. So m equals 5 means that I want to calculate the m equals 0, which will be 0, m equals 1, m equals 2, m equals 3, and m equals 4 numbers. So when you want the first 4 numbers in your calculation, you would set this equal to 5. Okay, so C is the array for the coefficients, and F is the array for the arguments of the complete series. Okay, so C is what we're actually trying to calculate, but we're initially just initializing an array of length m, and we're going to set all of those equal to 0, and then we will calculate each one by one and replace those zeros with the calculation. And the argument, this f argument, is going to be this n pi x over 2a. Okay, so this is what we mean by f. And the reason I chose f is because n pi over 2a represents the frequency of the sine wave. Okay, so that's why I chose f. And that's what we're calculating in this line of code. So this actually calculates the explicit frequencies for the complete set. So if I go over the index I over range m, what this will do is the first one will calculate 0 times pi over 2a, and that will of course be 0, which is why the 0th element drops out of the calculation anyway. And then when I is 1, it'll be pi over 2a, and then when I is 2, it'll be 2 pi over 2a, and when I is 3, it'll be 3 pi over 2a, and that's what we're seeing here when we let n run from 1 to infinity. We would get pi over 2a, 2 pi over 2a, 3 pi over 2a, and so on. So this actually calculates the frequencies, and that allows us to not have to type in a really long function in the integration algorithm. So here is where we actually do the integration. Okay, so here is where we integrate. All right, and we will set some values here, or make some comments here as we go. So up here we used I for our index. We could have used I here. It doesn't matter. I chose J. But again, so we're still going over range M. So we're going to calculate each coefficient in our C array over the number of M times. So M equals 0, M is 1, M is 2, M is 3, and M is 4. When M equals 5, it would go from 0 to 4. So this line right here is going to represent the product in the integral. Okay, so I went ahead and labeled this psi sub k, and this is np times the square root of 1 over a, and times the sine of the frequency times x. So this represents, I'm sorry, this is not the product of the integral. This is the complete set. I'm sorry. It's been a few days since I've coded this, so I apologize. This is the complete set. So psi sub k is np square root 1 over a times the sine of our frequencies that we calculated up here times x. So psi sub k represents this right here. Okay, and I went ahead and divided 2 over 2 to 1, but I left 1 over a again in case you ever want to change the width of a. This is the line where we actually calculate the product for the integral. Okay, so psi total is going to be psi prime, which we defined up here. So this was our original function right here, which is right here in the integral, multiplied by the psi sub k, which we just defined, which is right here. Okay? So this line of code is taking your original function, multiplying it by the indexed complete set, and this is what we're actually going to use in our integral. So z is going to be what we get, placeholder for calculation in Simpson's rule. So remember that to do Simpson's rule, you do the loop over your indices as such. So this is the actual loop over which we do the integral. So we take psi total and we take the value for each index in the range lowercase n, which we set to the number of data points minus 1, all divided by 2. And you take twice the first index minus 1, and then multiply that by 4 times the value of twice the index, and then add the value at twice the index plus 1. So then you add all of those up. You add all of those individual calculations up, and that's what this line does. And then you multiply by your length element, dx, or interval element, your x-axis increment, and then divide by 3. So if we want to comment on this line by line, okay, so calculates initial part of Simpson's rule result. Okay, and remember, once again, just reiterating the point, we're looping over lowercase n because in Simpson's rule this is the number of data points that you actually do use in the loop. Okay. Oh, and I should have mentioned in this line of code that the int function makes sure to or makes sure n is an integer. Let's put it that way. Okay, the int command makes sure that n is an integer, and we need n to be an integer because if n is not an integer, then if you try to do a for loop or any loop over something that's not an integer, it won't work because it needs to be indexed by integers 0, 1, 2, 3, 4, 5. So this ensures that this will be an integer, not a floating point number or a Boolean. And so we do need to make sure that n, lowercase n here, is an integer, right? And also, if you don't have, if this is not an even number, and this is another reason why I chose this interval of 1001, because when you use Simpson's rule, this n minus 1, and then you divide by 2, it's much simpler for Python to get a number that is easily converted to an integer, even if it considers it as a float, rather than having to try and round, okay, and force something that's not an integer to be an integer. So if I had just used 1000 for capital N, then I would have 999 for n minus 1, and then when I divide that by 2, that's 499.5. And then I'm trying to force that to be an integer, okay? So that's another reason why I chose this particular interval, was for this step as well, right? So that needs to be an integer. So this calculates the initial part of Simpson's rule. This is the actual algorithm. Simpson's loop algorithm, okay? There we go. I didn't want to enter. I wanted to do that. So now this calculates the result of Simpson's rule, right? And what this does is this sets, so remember that we defined our C array to be initially zeros, and now this is saying I want to define just a generic variable C sub j to be that to be the result of Simpson's rule, and then this line says, okay, now look at the array that I've named C and replace the jth element in that array with the result from Simpson's rule. So this replaces the jth element in C with the Simpson's rule result. Okay? And so now this is actually, this line of code is our coefficient. That we're after. Okay? This is the coefficient that we're after. And then this just prints each coefficient. Right? Okay. So then we don't want to do that. Let's do, there we go. So this line of code just creates the rest of the plots. Okay. So again, we're going to go over the range of m. This is the number of coefficients I wanted to calculate, and therefore that is also the same. If I wanted to calculate this number of coefficients, then that requires me to use that many of my complete set. So this line of code actually calculates each result in the summation series. Okay, I'm taking my coefficient that I just found, and I'm multiplying it by the complete set that we had defined right here. Okay, and so that literally is this right here. Right, that literally is that right there. So I'm taking my coefficient that I just calculated from this integral, and I'm multiplying it by the same index of the complete series. Okay, so that's what this line of code is. This line of code creates the so this creates the sum series. So after I find C1 and C2 and C3, this line of code actually performs the summation, right? So I'm taking C1 psi of 1 plus C2 times psi 2 plus C3 times psi 3 plus C4 times psi 4, and so on. Okay, so this creates the sum series. So this creates a subplot. Oh, that I should have mentioned something here. Okay, and I'll explain how the subplots work here in just a minute. So in the second subplot, what you're seeing is each individual of the functions that we calculate on the same graph. They're not added up yet. Okay, remember they're added up in the psi total. So in this, we're just seeing each individual what do I want to call this? Right? So we're seeing each individual coefficient multiplied by the function here. Okay, so we're just plotting each individual coefficient multiplied by the complete function at the correct index, right? And so the reason that this does this is because it's in this loop. So this loop does all of these calculations for m equals 0. Then it'll do all these calculations for m equals 1. And then it'll do all these calculations for m equals 2 and so on. And so I guess I should back up here. So what that means is psi, originally, we had set equal to 0. Okay? We had originally set psi equal to 0. So then when it calculates through this, for the first or the 0th index, if you will, remember c of 0 is 0, so psi is 0 the very first time it runs through that loop, which is why you don't see a 0th component here, but we don't have one anyway. But then when m equals 2, or when m equals 1, then it pulls the first element, or I should say the one indexed element from the C array that we just calculated up here, and multiplies it by the first indexed frequency. So this is the first coefficient multiplied by square root 1 over a np sine of 1 times pi over a times our x2 length. Okay. So that's why we're going from 0 to 2, because we're indexing this over the x equals 2 array. The psi total, this plus equals sign, for psi then says, okay, whatever psi was set to, I want to then add the next psi to that. So it basically takes whatever this plus equal sign takes whatever the old value of this variable was and adds the new variable to it. So for the psi, when m was 1, or I'm sorry, when m was 0, okay, when m was 0, psi was 0, right? This line of code would have given 0 when m was 0, because that means j was 0 and c of 0 was 0 and the sign of 0 was 0. And then, so it went through this calculation and nothing happened. Okay, but what it did, I shouldn't say nothing happened. I should say that this psi variable then got bound to the number 0. And this psi total says, okay, I want to add each psi value to psi itself. So it would then add 0. But then when j equals 1 and it runs through the loop again, this is no longer 0. This gives us a number, or an array, actually. This is actually an array of numbers. And so then that says, wait a minute, add that array of numbers to your previous value. And then when j is 2, this gives us a different array of numbers, and it adds it to that again. So that's why we get this iteratively added function right here. Okay, that's where we get this iteratively added function right here. It calculates each individual psi, each of these, and then adds them all up as we go along. Okay? And that's what this psi total is. Okay, it takes the previous value of psi. So if j were equal to 3, it would take the j, or the 3th indexed calculation here, and then it would add that to the 2nd indexed calculation and the 1st and the 0th. And then when m is equal to, or j is equal to 5, then it would take the 5th indexed calculation for this and add it to the 4th and the 3rd and the 2nd and the 1st and the 0th. So it's just a cumulatively added thing. Okay, so then we get these, we make these subplot commands. And so this adds or plots each individual coefficient times the complete function. So this actually gives us these waves. And so these represent the strengths of each of these complete set functions that appear in our result. So you can see that the second function actually seems to be a little bit stronger than the first function. And we'll actually see how that works here in just a minute. And then this creates the third subplot. And this plots the summed series of complete functions. Okay? And then this creates the fourth subplot. And this plots the total summed series by itself. Because this line of code is in a loop, it plots each individual psi total as it's calculated. So after the j equals 1 calculation, all you would see is the yellow line, or the one yellow hump here. After the j equals 2, we would see the yellow line and the green in this, and then all you would see is the yellow line and the green added together here. But because we have m equals 5, we're running several coefficients. And as we'll see, right, because I've argued that setting m equals to 5 means we're effectively taking 4 of the Fourier coefficients, but you only see 3 functions in the complete set here. And we'll actually see that it's because one of the coefficients is actually 0. And you can actually guess which one that is. It's actually the fourth one. It's really, 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 really small. It's effectively 0. And the reason for that, we won't get into the reason for that, but that is why you don't see 4 curves there, right? Because if m equals 5, then there should be 4 curves. One of the coefficients is effectively 0, so you only see 3. And then this line of code shows the total result. And this last line of code prints the sum of the coefficient array, and the sum of the coefficient array. In this case, in quantum mechanics, I won't prove this here. Maybe I will in a video upcoming. But in quantum mechanics, the reason that this line of code is important is because when you go through a calculation like this, what you should find, okay, because these Fourier coefficients actually relate to the probabilities, okay? The probabilities of making measurements of specific values. And probability cannot add up to more than 1. And it turns out that the square of these coefficients represent the probabilities. So what you should find is that the sum of the squares of these coefficients as you approach infinity should equal 1. So that is why we have that line of code there. Okay? Because if you get something more than 1, in this particular case, you know you've done something wrong. It's not cool. So this is the code. Now let's kind of bring this back out and go through what these results are telling us. So let's run the code. Okay, so here in this line, I've said print each coefficient. So we have m equals 5. We will have 5 coefficients. 1, 2, 3, 4, 5. Again, the first one will always be 0 because the sign of 0 is 0. And then the last line here is the summed square of the probabilities, or the sum square of the coefficients, which represents the total probability. So that's what this line of code is doing, and you can see that we get 0.9899. So what this means, if you were to do this quantum mechanics experiment, is that if you were to perform this experiment, you put a particle in a well and you expand the well instantaneously so fast that the particle has no time to respond, and you immediately make an energy measurement, you will find a 98.99% chance that you will measure the energy to be either in the ground state, the first excited state, or the second excited state. This is the coefficient of the ground state of the orange line. This is the coefficient of the green, of the second n equals 2 function, or the first excited state. This is the coefficient of the red, or the second excited state, and so on. And as I said, one of these is very close to 0, right? 9.3 times 10 to the negative 9. When you compare that with 0.6, 0.7, 0.36, this is effectively 0. So that's why you don't see anything form here. And something is really striking if we actually plot, if I add this line of code to this last line here, we can actually see how this will be overlaid. Okay, we can actually see this function overlaid on this one. And by the way, the K dash means I want my line to be black. I want my curve to be black, and I want it to be a solid line. And so that's why this is a black solid line. Python then arbitrarily chooses the colors for the subsequent graphs unless you specify. And it will usually, when you have just one, it'll default to blue. So that's why this last one is blue. But if I run this again, then you can actually see how the overall result starts to approximate the original function, which is actually kind of cool. So one more thing, and then we'll just kind of run this a little bit more. But the subplots, okay? So the subplots 2, 2, 1, what does that mean? When I make a subplot in Python, the first number is the number of rows. The second number is the number of columns. I want 2 rows, 2 columns, and then I want this to be the first plot in the series. So it plots from upper left and then goes across and then down and across. So this is subplot 1. This is subplot 2, subplot 3, subplot 4. So for my other subplots, 2, 2, 2 means I'm still doing the same series, 2 columns, 2 rows, and I want this to be the second graph. So it creates this graph right here. And then subplot 2, 2, 3, 2 rows, 2 columns. I want this to be the third plot. And then 2, 2, 4, 2 rows, 2 columns. I want this to be the fourth plot. Okay, so the really interesting things happen when you add more and more terms here. So what if we add 20 terms? So I'm going to calculate 19 coefficients. Okay, I'm going to calculate 19 coefficients. And here we are. And you can see, now you can actually start to see a pattern kind of start to emerge. After we get done, so this is the n equals 1, this is n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, 7, 8, 9, 10, 11, 12. After you get past the n equals 2, it turns out your odd coefficients will effectively disappear. Okay? Your odd coefficients will effectively disappear after n equals 2. So then you only have the n equals odd coefficients to worry about. But notice, okay, now we've got a lot more coefficients in here, or sine waves in here. And that means that some of our coefficients did not disappear, and that's what we're seeing here, right? Even though this is really small, it's still not negligible yet. Not in the same way that 3.7 times 10 to the negative 8 is. And now when I add 20, look at this. You can still see a little bit of wiggle down here. But other than that, the series of complete functions with the correctly calculated coefficients is nearly an exact match for our original function. Okay? Nearly an exact match, which is really cool. So this is how you can calculate Fourier coefficients. And some things to take note of, okay? Some things that we haven't really talked about but are important for higher level computation are, is the interval that I chose right here really appropriate? Now, it's easy for the computer to handle 0.001, but is that really the appropriate value? Pardon me. Is that really the appropriate value? What is the most optimal increment to minimize rounding error, okay, in your calculations? Now, that is a non-trivial topic, and it's one that I won't cover in, these introductory videos, but it is non-trivial nonetheless. But for quick and dirty calculations like this, we don't have to worry about that too much. And you can even, you can choose whatever interval you want here. I would highly recommend making this odd, so that way you make this calculation even from the get-go. But you can use whatever increments you want, as long as you don't use increments that are too big, right? You wouldn't want to use 3 data points, right? What happens if I choose 3 just to be obnoxious, right? It might even break, okay? Yeah, so it didn't exactly break, but you definitely don't see the nice smooth curves that we want or that we're after. So choosing your number of increments across your x-axis is non-trivial. Choosing your increment is non-trivial. But as long as those are chosen appropriately, you should be able to get fairly good results. And so, what if, just out of kicks and giggles, let's take 30. And I won't take more than 30 here. But what if we do 30? Can we get rid of those wiggles a little bit? You can still see them just a shade, right? They're still there just a shade. But in any case, as you can see, this starts to approach the desired result very, very rapidly. And when you're talking about, series that should converge at infinity, 30 is far less than infinity. So getting the convergence at this level that soon is rather remarkable. And that it speaks to the power of the complete functions. Okay. Now, I understand that this is a bit of a higher level than the computing that I have done before in the videos, but hopefully the meat of what is going on is understandable, right? Hopefully the meat is understandable, and you can use this technique to as long as you have a complete set. As long as you have a complete set, these functions right here, as long as you have a complete set over some interval, then you can calculate or approximate a well-behaved function if you can calculate the Fourier coefficients. And that's what the integration technique does. And there are better integration techniques than Simpson's rule. That's another thing I should have mentioned, right? Not just the interval issue or the increment issue, but is Simpson's rule the appropriate integration algorithm here? And it turns out that it's really not a bad one. And again, it is a good median or compromise between feasibility and codability and accuracy. So it's not the absolutely most accurate integration algorithm out there, but it is a very, for most applications, it's very accurate. And it is not terribly convoluted, right? The actual integration is really 3 lines of code, right? The integration is found right here in these 3 lines. So technically, these, if you want to include the placeholder of 0, but 4 lines of code are the integration. And so that's really not convoluted at all. And it gives very accurate results. So even if the math may have been a little fuzzy, I hope you found this tutorial helpful. And in the next video in the series, well, I haven't decided exactly what I'll do yet. But it might be slightly higher computationally like this one was, employing a bit more sophisticated physics and math. By the way, the reason I like this problem and the reason I'm proud of this program is because this particular problem, the expanding well and calculating the coefficients, now was a problem on my PhD qualifying exam, and we didn't have to calculate out everything explicitly by hand, so we didn't actually have to calculate these numbers out. Doing it by hand is actually a bit of a pain, but we at least had to set up the problem and show how the calculation would be done. So we basically had to set up this integral. We had to set up this integral. And even getting there is really not all that trivial, right? It's really not all that trivial. But in any case, I really like this because this was one of my PhD qualifying problems. And here it is in computational form. And we know that we have the right answer. We're calculating the correct coefficients because, number one, their sums, the sum of their squares, I should say, is approaching 1. And the function absolutely is approximating the original function that we were looking at in question. So I really like this problem. Again, this is not the most efficient or most beautiful way to code this, but I do think that it is a step-by-step / brute force method that if you can think through each step kind of as a little mini problem to solve and then conquer that mini problem, then by the time you get to the end of the code, you feel like you've conquered a mountain. But once you understand this code, you can then move on to other bigger and more interesting things too. And then you can also challenge yourself to go back and learn more efficient ways to do this, right? So with that in mind, I hope you enjoyed the video if you've stuck with me this long, and we will talk to you next time.